जनगण मन अधि
Base.
Happy morning. Happy morning. To improve the golden moment of opportunity and catch the good that is in our reach is the greatest art of life. We welcome you all to the day 3 of International Interdisciplinary Virtual Conference on Breakthroughs and Approaches in Contemporary Scientific Research, organized by PG and Research Departments of Chemistry and Physics, PSGR Krishnamal College for Women, India, in association with the Departments of Chemistry and Physics, University of Dar es Salaam, Tanzania. To begin with, we have technical session 5. May I now request Dr. P. Kanchana, Assistant Professor, Department of Chemistry, PSGR Krishnamal College for Women, to introduce the eminent speaker, Dr. R. Nanda Kumar, Associate Professor, Department of Applied Chemistry, Karunya University of Technology, Coimbatore.
A pleasant good morning to one and all. I deem it an honor to welcome and introduce our speaker of the session, Dr. Raju Nanda Kumar, Associate Professor, Department of Applied Chemistry, Karunya Institute of Technology and Sciences, Coimbatore, India. Sir did his PG at PSG CAS, his MPhil and PhD at Bharatiyar University, Coimbatore. He worked as postdoctoral research scientist from 2004 to 2006 at University of Science and Technology, Pohang, South Korea. He did his second postdoc at Eva Women's University, South Korea from 2006 to 2009, followed which he worked for the third postdoc at the same university till 2010. He has won many awards and honors. To mention a few, Achievers Award 2017 at Karunya University, Coimbatore, Outstanding Faculty Award for Medicinal Organic Chemistry in 2016 by Venus International Foundation, Chennai, Mark You Who's Who in the World, Brain Korea 21 Fellowship, and so on. Sir is an editorial board member for nearly 12 journals like Journal of Photochemistry, Journal of Analytical and Applied Chemistry, etc. He is also a reviewer of many journals under ACS, RSC, Elsevier, Ville, Springer publications. Sir is a member of many professional bodies like American Chemical Society, Materials Research Society of India, Indian Council of Chemists, Indian Science Congress Association, American Biographical Institute, Korean Chemical Society, etc. Sir is a Board of Studies member of nearly 12 colleges. He has 141 publications, 10 patents, and 3 book chapters to his credit. Sir has completed many projects funded by DST and also from Karunya University. An added feather to his cap is that he is operating a project funded by DST SERP to a tune of 34 lakhs. We are fortunate to have such an eminent researcher and an achiever as our guest speaker today. On behalf of Department of Chemistry and Physics, I once again extend a warm welcome to Dr. Nanda Kumar, and I request him to enlighten us with his research expertise. Welcome, sir.
Thank you, ma'am. Over to speaker. Sir, you can start sharing your screen, sir.
Thank you, madam. Am I audible and my slides are visible?
Yes, sir, your slides are visible and you are audible.
Thank you so much. Okay. So good morning, everyone, wherever you are. Good morning, good evening, good night sometimes. It's a pleasure meeting you all through the virtual platform. During the pandemics, the academics and the research is going on. So thanks to the technology, the software guys have developed with the help of the internet and all those sort of technology things. So we are basically science persons. Before the start, I wish to thank the management of PSDR Krishnamal and the University Dar es Salaam in Tanzania for giving me this opportunity to present my research expertise and what I'm doing on the fluorescence chemosensor at Karunya University. I also wish to thank the head of the Department of Chemistry and Physics and my friends there, all the faculty members and students. It's a great privilege and pleasure to be here. Okay, so without wasting much time, so let me get into the topics of today. What I am going to talk about is organic materials, modular fluorocalorimetric chemosensor for varied applications for this international interdisciplinary virtual conference on breakthroughs and approaches in contemporary scientific research. So I'll be talking about the fluorescence and colorimetry, that is the fluorospectrometer and the UV. Based on that, what we could achieve for the past decade. So luminescence, it is the emission of light by a substance. Hope everyone know this. So it occurs when an electron returns from the electronic ground state, electron returns to the electronic ground state from an excited state and loses its excess energy as a photon. So based on this principle, this total fluorescence and works on. So the basic principle here is the molecules are excited from the ground state to the electronic state. From there, it releases when it comes down. So these excited species gives emission spectrum that provides the information for quantification and qualification, from wherein we have done all those things. So talking about luminescence, earlier age, what we call it as the bulb and the candle. So they glow because of incandescence. So it is the emission of light due to the high temperature of an object. But that was not an efficient way to produce light because most of the energy is emitted as heat. You might have seen that bulbs, right? The incandescent bulbs, when you touch it, becomes heat after a long time when it's burned. So thus light produced by incandescence are called as hot light. But luminescence is the emission of light at normal or cooler temperatures. So the mode of excitation matters here. So different mode of excitation has different terminology. For example, if you excite the molecule electrons from the ground state to the excited state by heat, supplying heat, then you call it as thermoluminescence. By electric field, you call it as electroluminescence. By chemical reactions, then you call it as chemiluminescence. Like sound waves, it is called as sonoluminescence. So and so on. There are many. By particles emitted from radioactive materials, then it is called as radioluminescence. But what we are going to focus on photoluminescence. That is, you give light. With the help of light, the electrons are excited from the ground state to the excited state. So fluorescence and phosphorescence comes in that. A brief history. So the term fluorescence was introduced by Sir George Gabriel Stokes, a physicist and a professor of mathematics at Cambridge in the middle of the 19th century. So he's that professor, Sir George Gabriel Stokes. So he coined the word fluorescence. That is, there are naturally occurring chemicals like fluoride, fluorspar, calcite, columnite. There are many naturally occurring minerals which glow. So opalescence means glow, and these are all the minerals which glow. So combine these two, fluor from fluorspar and essence from from opalescence. He coined the word as fluorescence. So it basically has two things. One is the molecular recognition at one part, and that should be converted as a signal, maybe optical or thermal or physical or whatever signal you want. You have to convert that and take it quantitatively. So this spectroscopy we can broadly into emission and absorption. So the emission again into molecular and atomic, and that to the photoluminescence. So we have fluorescence and phosphorescence. So that fluorescence can be measured with the instrument spectrophlorometer. So I don't want to go to the instrumentation part. So everybody might have been familiar about the fluorescence, that is the Jablonski diagram. So from the ground state, the electrons are excited to the singlet state, first or second. From there, it comes back, releasing some energy, so which we call it as the radioactive decay. That is nothing but the fluorescence, and the lifespan is 10 power minus 9 to 10 power minus 7 seconds. So besides that, there are many non-radioactive decay also. And you know this, when it goes to the triplet state, then it is called as intersystem crossing. And then inside itself is called as internal conversion from S2 to S1. And then from the triplet state, when it comes to the ground state, we call it as a phosphorescence, or you call it as delayed fluorescence in general, but that is not the correct term. But this is a pretty old fluorescence Jablonski diagram, but these days the Jablonski diagram has been modified. So you even have RIC, that is reverse, RITC, reverse intersystem crossing, by thermally activated delayed fluorescence. So when it is again converted from triplet to singlet, and from there it emits, so they are called as thermally activated delayed fluorescence. So that's what we cannot use this delayed fluorescence as phosphorescence. Okay, so this is also another terms, and they have many other research going on those areas particularly. So that is, now students who have studying the Jablonski diagram, look out for the modified Jablonski diagram, which includes this TADF, etc. So based on this, we are working. So this absorption, this is the absorption peak and the fluorescence peak, and these are of course the mirror images. So the spontaneous emission of radiation from an electronically excited species or from a vibrationally excited species, not in thermal equilibrium with the surroundings, we call it as the fluorescence. Right, so let us come to the mother nature. This is what I told. There are many natural minerals available, like columnite, calcite, fluorospar, fluorspar. Everything glow with when they are hot in conditions. Fluorescence. Then we go to the deep sea, what you call abyss, and that level. Naturally, these fishes, this is a squid fish, it gives a counter illumination like this. So it glows here. So when the prey comes here, it can easily attack for it. We have a lure prey. It produces a small glowing here. So the other fishes comes and looks after this, so it can easily have its prey there. And then similarly, they sometimes glow, and then suddenly they will not glow. They stun and confuse the predators or prey. These are all the fishes which are available, and the use of a red light here. So the red light attracts the prey for them, and then for mating. So when they glow, they are ready for mating. So like that, these are all fluorescence, or in the term luminescence, which is happening in the sea. So from the deep sea, now we shall come to the crime lab. You can see, you know well about these crime scene investigation, your fingerprint scanning and all those things. For that also, these fluorescence is used. We have seen how organisms can use luminescence, but now how we can use the luminescence, that is what this luminol compound. So this is a typical luminol compound. This is not fluorescence, but when this bond is broken with a catalyst like this, so they emit light. So that can be broken by any free radical like H2O2, which creates that free radical like H2O2, etc. So this is there in this ion can catalyze this one for the bond breakage, and the glow happens. So it is there in blood, so bleaching powder, feces, urine, horseradish, etc. So when blood stains are there, when you spread the luminol there, so the ion in the blood catalyzes this luminol, and then when you pass a particular wavelength of light, that gives you glow. So you can easily find out whether there are blood stains or not, or whether there is bleaching powder or not. Everything is useful in forensic sciences. So like these type of things, things can be taken with the help of luminol. I'm just telling a simple example with one component. There are many other things like that. And even the dissociation of phenolphthalein helps in solving the bribe trap case. So like when they give money, they spread the phenolphthalein powder there in acidic conditions, and then later on when you dip into the base conditions, you get the pink color. From there they can go for TLC, UV, HPLC, IR, and make sure that this guy has got the bribe. So there also it is useful just by color changing. So this is colorimetric I'm talking about. The previous one is the fluorimetric. And the most recent advancements are molecular imaging. So you can see this is the normal surgeon's view. This is the normal surgeon's view. He is not able to locate where the tumor cells are. But this is the surgeon's new view. So where the glow happens. So you can easily, the surgeon can see, okay, these are all the areas where he need to do a surgery or something like that. Okay, so targeted agents. So this molecular imaging, for all these things, fluorescence is useful. I will go to this one. So in this, you can see the surgeon easily can see which part to be removed in a surgery by the help of this fluorescence. So this is a multidisciplinary research, this image guided surgery. 5 people have to be there. So one is the chemist, to develop the fluorescence molecule. The other one is a biologist to find out what type of protein is there, where the protein binds with our molecule. And the third one is the physicist to find the exact wavelength of light wherein it can glow at that particular wavelength. So physicist, a biologist, a chemist, and a surgeon. He has to operate that part. And the fifth one is the investor, because without the investor, we cannot do this type of research and conclude on these things. And after that, you have laparoscopy, endoscopy, colonoscopy. There are many, many things. So that is different. This is the molecular recognition. You have to recognize that particular cell which is creating a problem with the help of a molecule. When they both join, what signal you get? So that is what the fluorescence. So this is what a multidisciplinary research wherein many MRI and CT, PET and everything is going on. So another one is the diagnosing diseases. So amyloid PET, positron emission topography with computer topography. So this is imaging in aging. So for your Alzheimer's disease and Parkinson's disease, etc. So this is normal, and you can see there are some red spots, which is normal aging. So amyloid positive. So they may be having Alzheimer's disease or Parkinson's disease, etc. So this is what I told you, that there is a brain tumor. So you can see how glow it is. So similarly in NIR fluorescence and the color images, when you merge, you can easily see where is the ovarian cell cancer cells are located. So if the surgeon can easily remove that part of things, or he can easily give the treatment for that. So these days you have the fluorescence marker as well as the medicine to that. So diagnosis as well as therapy, both together, which we call it as theranostics, has come into existence. So you can have you can diagnose what is the problem, as well as you can have the medicine also, both in a fluorophore. Okay, so together, so these type of things are called as theranostics. So this is the lymph node identification. So these lymph nodes are very much needed, because to see or to check whether the cancer is spread to the other level or not. These lymph nodes, so they are called as sentinel lymph node tracking. For this, indocyanine green dyes are used, and they are glowing. So if it is there, we can take this and check for biopsy and see whether it has been gone for other areas, it has been spread or not. For these type of things, this fluorescence is very much useful. And of course, if you take for agriculture, chlorophyll fluorescence imaging for early detection of plant diseases. So you can see here, this is the degree of infection is 90%, but in this case, you can only little, so it is 30%. So chlorophyll fluorescence analysis and chlorophyll fluorescence imaging is early detection of plant diseases we can do with the help of this fluorescence technique. So you all need is fluorescence molecule for that. So coming to the colorimetric side, you have known about the pregnancy kit test. So when you have both the lines like this, positive, and these are all negative. So I think when a woman or a lady is conceived, the early morning urine, if you have 2 drops of urine, if you put in this part, excuse me. Hello, am I audible?
Sir, please continue, sir. Some background.
Thank you. Thank you. Thank you. So when we have particular, early morning urine. So if you have 2 drops here, so it shows whether she is conceived or not. The responsible thing is the human chronic gonadotropins. So that will be secreted a lot when a lady is conceived. So you need to capture that with the help of a organic molecule. So when they capture, they give the color here. So earlier days, they used to take that urine and put it inside the rat or a rabbit, and then they will dissect the rabbit's reproductive organs, and then they check whether it is the lady is conceived or not. But these days, you can have within minutes, you can see whether she is conceived or pregnant or not. So you need to have these type of colorant signals. Okay, so for that, it can be used. And then blood sugar test. Early days, we need to go to the laboratory and give our blood and wait for 3 to 4 days to check your sugar. But these days, it is very, very easy. Within minutes, with the help of a glucometer, immediately you can prick in your hand and you can just put it here and you can see. So the responsible thing here is the boronic acid group. So these groups are responsible to capture the glucose, and it gives signal. So this signal, this chemical signal, is converted into the optical or into a values or into a graph. So whatever it is, we can convert and take it. So the main responsible unit is the boronic acids, and lots of research is going on this boronic acids. Right, so this is the blood glucose chart. You know about this. The normal fasting is 80 to 100, and after eating 170 to 200, there are a lot many on these areas. So with the help of colors, now we have got a pH paper, like a pH paper, just a strip of paper. So in that paper, if you just pass your urine and if the color changes, it will tell you whether you're diabetic or not qualitatively. And later on, you can take your blood test and check the exact values. But immediately you can see with the help of a strip test. There are more and more of these type of strip tests are available at present in the market. And next, coming to my focus is on this ion detection. Metal cations and anions is what I am doing at Karunya in my laboratory. So see this is a strip of paper and it tells so much mg per liter or ppm of zinc is there just by the color change. Colorimetric visual detection by UV itself, you can see, or your visual detection by the change of the color, you can tell how much amount of zinc is present in your body. And this one, by this image itself, you know very well, it is the goiter problem with the help of iodine. Wherever I go, wherever I give a talk, I used to ask one question here. Everybody I think, will be using iodized salt. So what is the need of this iodized salt? Basically, if you are anemic, if you are very low, if you are having very low content of iron in your body, then you take iron tablets. That's fine. If you're low in calcium content, you take calcium tablets. That's fine. Or your food stuff, accordingly, you take that is fine. But you're normal, hale and healthy. And why you want to take this iodized salt? What if you take non-iodized salt? That's a question to all the audience. So those who are listening, so please, you can give me an answer why we have to. So any defect to correct to take is okay, but we are taking. So will it not be additional in our body? I'm still curious about this. But for the past decade, we are all consuming iodized salt. But now the government is planning for ionized salt, IRON, ionized salt, instead of iodized salt. I still could not figure out the reason for this. Okay, so how you could find out whether there is any problem, goiter problem, or the iodine deficiency or increasing, you can have these type of tests. Or heavy metal tests for cadmium, mercury, silver, etc. And like that for copper, for magnesium, for iodine. So immediate, you need everything immediate. For that, what type of sensors you can use. And this is more important as drug and chirality. So thalidomide case in 1950s in UK. Many students, many children born with deformatives like this, what you call it as teratogenetic. Okay, this one, because they have given the racemic mixture R&S together for the pregnant ladies to avoid that early morning nausea and vomiting during pregnancy. But what happened, certain children were born good and certain children were born with defects. That's what we call teratogeneity. So that is because later on, after 10 years, after death of many people, then they come to a conclusion that the R form prevents vomiting, but the S form is dangerous. It creates the deformative. So this is the R enantiomer, this is the S enantiomer. So our body is amino acids, which is made up of L amino acids, 22 and plus 2 now 24 amino acids. They are the fundamental building blocks of our body. Amino acids, which forms the dipeptide, tripeptide, and then polypeptide, which forms the proteins and the muscles and everything. So the fundamental building blocks is your amino acids. So that amino acids is chiral in nature. So your drug should be chiral. So much important is this drug. So you can easily discriminate whether it is L or D with the help of fluorescence and visual seeing. And also highlighter colors. So you have, this is pyranine dyes, you have yellow color, you have rhodamine with a pink color, you have a triphenyl with a blue color. So these colors are also glow, you can use for that. And this is very interesting, is your voting. So previously they will put some ink in your here and then you can see for whether you have voted or not. But maybe sooner you'll be getting like this. They will just draw only when you pass light, it will glow. So only when you pass light, it will be glowing. So whether you have put your vote or not. So for this voting, invisible ink can be produced. So when you pass that exact frequency of light, you can check. So that cheating can be avoided. So there is a lot of demand in industry. So you can see this for all these things: computerized tomography or magnetic resonance imaging, positron emission tomography with computer tomography. For all these things, this optical fluorescence imaging is a must. You can see here for hospital and clinical, more than 30%, this fluorescence microscopy is in great demand. Besides, you have pharmaceuticals, biology, and academic and other things. Coming to my point is metal ions in human body. So this is what we are doing here. So metal ions in human body. So there are many metals, essential elements like calcium, phosphorus, sodium, potassium, magnesium, etc. Trace elements like 100 mg per day is iron, copper, cobalt, zinc, etc. So their importance I have given for sodium and potassium regulating body metabolisms. It's very much important because of the potassium channels and ion channels where they move your dehydration and a lot more on that area. And calcium, you know very well, for the strengthening of bones and teeth, or else you will be developing these arthritis, osteoporosis, and all those things. And copper, metalloproteins and metalloenzymes for redox reactions, and iron, you know, oxygen carrying capacity of heme inside the body. 4 units of myoglobin joining to form the hemoglobin and transport of that ion inside. And these zinc for enzyme regulators and neural signal transmissions. If they are in particular level, that is at the exact level what the body requires, no problem for you. But if it is more or less, there creates the problem. So the disorders due to the deficiency. So if you have deficiency in iron, you become pale and you become anemic. It should be somewhere around 15 to 17 for male and 12 to 14 for mg per L for female. But if that value differs, either high or low, you are in trouble. So it should be incorrect. You lead to kidney damage, diabetes, heart failure, and finally fatal. Similarly for zinc, and copper creates Alzheimer and Wilson's disease. So you see biologically important metal ions in your day-to-day life. Just in a kitchen, you'll be using cadmium, you're using copper, you're using silver, you're using all even mercury in the kitchen. See, with the help of a fluorescent lab. So these are all day-to-day you're exposing yourself. But you should balance. So these essential elements, these are called as macro elements, and these are trace and ultra trace elements. So this is the chart taken from World Health Organization, how much it should be in your body, their values. So what are the effect of metal ion? See, Pb, it should be 121 milligrams. If it is excess, it leads to plumbism. And similarly, cadmium, it is excess. If it is excess, you need to high boiling point. Like chromium, cancer, you know very well about our CLRI, Central Leather Research Institute. They are doing a lot of chromium, the tanning of leather. So you need to find a sensor for that chromium, how much exactly your body needs and how much you are there in your body. All what I'm talking about is fastness. So similarly, you have tin, bismuth, beryllium, etc. And the deficiency, see iron deficiency, anemia, and then zinc deficiency, dermal disorder, and so on. So this is effects of silver. You have all sorts of problems, from asthma to bronchitis to cancer to disease known as etiology in kidneys, liver, and autoimmune diseases, everything, dermatitis, everything creates when you have excess of silver, when you're exposed to excess of silver, or even if it is reduced. Similarly, effects of aluminum. You go for dementia, damage to the CNS, central nervous system, and then it acidifies the oil so that the agricultural crops will not be good, and then effects on fish. And of course, you consume your fish and you will be having those sort of problems. And then you have lungs problems, kidney problems, etc. And this one is effects of mercury. So everybody know about the Bhopal tragedy which happened in India. And this is one such case which has happened in Harada at Japan in 1960s. So in the Minamata Bay, there were methyl mercury release in the Minamata Bay. So there were baffling systems happening at the time for all the children and all the people. Nearly thousands died, and still they are undergoing that problem. It is because of the methyl mercury release there. So that mercury, cadmium, and silver, what we call the heavy metals, we need a sensor to detect immediately. So these are all the effects. So see here, cancer due to metals, beryllium, lead, where it is used in lipsticks. So thallium, arsenic, and then organs are affected by cadmium in kidneys, skins, lungs, bone, etc. Arsenic cancer, and then peptic ulcer due to iron. It's just inside your body. So these are all due to the metal. So your body needs everything to be balanced. If not, these guys will be interfering in your body's proper biological mechanisms. So as I told, any metal having the atomic weight greater than sodium, you classify as heavy. Generally highly toxic as lead, mercury, and cadmium. So we need to have sensors. So basically, what is a sensor? I'm coming to this part now. A sensor is a device that measures a physical quantity and it converts it into a signal which can be read by an observer or by an instrument. Basically, we have 5 different sensors, you know very well: eye, ear, tongue, and nose and skin. So that is by nature we have. So what we could do synthesis. So a chemosensor or a chemoreceptor detects certain stimuli. That stimuli may be heat, pH, optical, anything like that in biology and environment, and that gives the signal based on that. There are a number of different types of sensors in the present scenario, depending upon the techniques they are using, like heat sensor, pressure sensor, motion sensor, moisture sensor, gravity sensors, and then vibration like that. One among that is our fluorescence-based chemosensors. So these fluorescence-based chemosensors recognize biologically and environmentally important metal ions. I told you, particularly, you need to have sensors for mercury, silver, etc. So these are that. You can see all with the instruments I have given you, which are facts. So you have temperature, oxygen, pressure, motion, and then one among that is your chemosensors. Right, so that is that part. So I've told about the fluorescence importance, I've told about the UV importance, I've told about the metal importance, and then I told about the, what is that, what are the different types of sensors available. Now, what type of science we are using to detect that? So this is called as supramolecular chemistry. So we have molecular precursors, small molecules. They join together to form a molecular chemistry, macromolecules. There are several macromolecules. I don't want to come up that. Like we have cocorbituril, we have cyclodextrin, we have calixarine, we have pilarine. So we have many, many macrocycles. So you create a macrocycle like this. So this is called as a host. And this will capture the guest here inside. But this is called as chemistry. These are called as chemistry beyond molecules. So there are nearly in between 3 decades, twice Nobel Prize has been awarded for this supramolecular chemistry. Professor Stoddart, Feringa, and all these guys. I don't want to put all those history because of the want of time. So later on, if any other time is provided, so I can talk about that supramolecular chemistry later. So now, just a hint I'm talking about. So these are called as chemistry beyond molecules, and absolutely there are no covalent, ionic, or coordinate or metallic bond between the host and the guest molecules. It is just the non-covalent interactions between the host and guest, like your hydrogen bonding, electrostatic interaction, ion dipole, 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 or hydrophobic interaction, or weak van der Waals force, London forces, etc. With that, it will be staying. So with that concept only we are using for our sensor. So that is what this. So this, if you take a host molecule, and these are all the guest molecules, only this guy particularly fits inside this, and this one you call it as selectivity or the molecular recognition. This can be applied for everything. So we are concentrating on metal basically. So this is a host molecule, that is the chemo sensor, and this is the metal ions. And when this guy bind to this, we get a complex. From there, we get different type of signal, either fluorescence quenching or enhancing or shifting, bathochromic, hypsochromic shifts, anything takes place. From there, we do our thing. So here, the shape and size matters. That's what mainly. So this is the shape, this is the size. So coming across the down the group, when you take lithium, sodium, potassium, rubidium, cesium, francium, or the magnesium, calcium, any group, if you come down the group, all the cations are almost spherical. Only thing is the size differs from small to bigger. But at the same time, if you want to develop a receptor for anion, it is very difficult because they are sometimes octahedral, pyramidal, planar. So there are all are in different shapes, nitro, phosphates, everything are different. So it is very difficult to have a receptor for anions than for a cations. So this part is called as selectivity. So the shape and the size should be complementing each other, and also they should cooperate with each other. Then only these type of molecules will be forming, because we are making these sensors in the nanomolar level or micromolar level, not in the bulk scale. So what is a chemosensor? So organic molecules designed to bind and sense small molecules or metal ions. So this is a fluorophore, and then this is a linker, and this is ionophore. This is the basic design of formation of a chemosensor. So when the metal ion has its interaction with the ionophore, there is a change in the fluorophore. As I told, either enhancement takes place, or quenching takes place, or shifting takes place, some sort of signal you get it. So this generally, this fluorophore together with this ionophore, it is called as fluoroionophore. So we conjugate these ionophore, and so this ionophore is the metal binding unit, and the fluorophore is the repeating unit. So this is what called as the molecular recognition here, and this is the signal transduction here. So both connected together you get. So you can tune around, or you can play around with the linker. That's what I have put it as modular. That means you can change the linker, you can change the fluorophore, you can change the ionophore according to the metal you need. So we have 3 different approaches, so which correlates with the title of the conference. So there are 3 different approaches to the chemo sensor. So this is the chemo sensor bearing a signaling subunit and binding site. So this is a fluorophore and the linker, and this is the ionophore which binds. So once it binds, there is a change here. Either it glow, I have shown here as glowing, so that is switch on, we call it as. Sometimes it may be a switch on, but after binding, it may not glow. That is called a switch off sensor. So switch on or switch off sensor. So it be a chemo sensor is bearing a signal subunit and a binding site. That is one type. The second one, the chemo sensor and an indicator. So these 2 guys will not glow, but once when it captures the metal or the guest molecules, the indicator is displaced and it started glowing, or vice versa. So this is called as displacement approach or indicator displacement approach. This is the second way. And the third one is called the Chemisometer or dosimeters. Here, the host molecule reacts with a guest, and there is a chemical reaction takes place. With the help of a chemical reaction, you have a fluorescence change, either enhancement or shifting, etc. So these 2 guys, the A and B approaches, are a reversible process. You can use this again and again and again. But this guy is an irreversible process because there takes place a chemical reaction, and once done, you have to throw it. So that is, these 3 are the major approaches. Inside, there are many. So these 3 are the major 3 approaches in designing a chemo sensor. So this is a cartoonic picture. So this is what the host molecules, as I told. So you have many different guest molecules, maybe like metal, this may be iron or calcium or magnesium. So only the ion, the shape and the size fixes to the host molecule. So when that exactly fixes, there is a change in the fluorescence of this fluorophore, so that can be quantified. So that is what happening. So the basic working mantra is, if there is no interaction between the host and guest, you do not get informations. So the mantra here is, there is no interaction, no information. There should be an interaction between the host and guest, so you get a value here. So this is a cartoonic representation of these chemosensors. So this, I am mainly concentrating on anion, cation, neutral molecules, and chiral recognitions. For these 2 is my major area, the applications of chemosensor. But it can be used for sugars, as I told you, for detecting glucose, fructose, etc., and for carbohydrates, and then for biological molecules, DNA, RNA, BSA, boron, C1, albumin, and all these things, it can differentiate with the help of that. For explosives, nitroaromatics, TNT, DNT, and for all those things, and drugs and pesticides, we can develop a sensor for endosulfan for agriculture purposes, and then for gases, dyes, pigments, and then for microorganisms. Still, this is a challenging area. Once if you are into a fever, maybe even COVID also, once if you are into fever, you have to take the blood and give to the microbiology laboratory, and they take 3 days for the culture. And then they come out and tell it is because of gram-positive bacteria or gram-negative bacteria or Salmonella typhi or Aromonas hydrophila. So it takes 3 days. Imagine you develop a sensor and a drop of a blood or even a saliva or a urine or in any sort, or even a sweat. And you can immediately identify your fever is due to this type of bacteria, or it is due to a virus, or it's due to a fungal. It's still a challenging area. Still, we are going to the lab and take culture. It takes 3 days, and then only we come to know it is because it is a typhoid fever. So this, if you could find a good sensor, it's a good thing for that, problem solving for humankind. So why these chemosensors when there are several other methods? You need to address that because it is low cost and it is widely available, and it gives high selectivity because that is more important in our body. All sorts of metal ions are there, but you need to particularly trap ion. So the selectivity is important there, and sensitivity. That's what I'm talking about. Up to nanomolar or femtomolar or picolever or even attomolar, it is good. So cost will be reduced and time will be reduced, and rapidity and ease of measurements in seconds, in minutes, if you tell the result. As I told about thalidomide, so the chiral discrimination is important. So it is an efficient, economic, and effective sensor. So you can detect all sorts of molecules. I have already told the applications. So operational simplicity, you can have a small portable machines wherever you go, you can take that. And then rapid response time, cost effective, low detection, etc. Right, so that is one part. Next, coming the science background of the chemosensors, concepts and mechanisms. There are a lot. If I want to take these concepts and mechanisms, I need another 2 or 3 hours to finish all these things. I'll just go through this. So fluorescence effects, as I told you, This is quenching mode, and this is enhancement mode. So this is a fluorophore generally. After binding with metal ion, it may enhance, or it may give a good fluorescence, but after binding with metal ion, it may quench. So this is called a chelation enhanced quenching effect. This is chelation enhanced fluorescence effect. Enhanced. So there are many other concepts like charge transfer, energy transfer, excited state intramolecular proton transfer, ESIPT, CN isomerization, ARE, aggregation induced quenching emission, and then chemisometers, and excimer, excited state dimer, and excited state complex, exciplex, and then electron transfer, etc. Based on this, there are several researches going across the globe. So these electron transfer can be further divided into paramagnetic fluorescence quenching, that is again into energy transfer, EET, and fluorescence resonance energy transfer, photo-induced energy transfer. When coming to the charge transfer, photo-induced charge transfer, metal to ligand, ligand to metal, twisted intermolecular charge transfer. So those are all the concepts which I've already explored, and they are there in the literature when you see the journal publications. There are several unexplored fluorescence concepts like interference of triplet excited states, upconversion fluorescence. These days you can see many papers on this upconversion fluorescence, and you have proximate effect on fluorescence, you have fluorescence polarization, you have exciplex formation, and finally the present stage is called as the unknown mechanisms, nanocomposites, for these type of things. Still yet to explore what type of mechanism is taking place in that nanocomposites when you deal with these supramolecular chemistry, supramolecular nanocomposites. Okay, it's still unknown mechanisms, but there are many researches going on, and it's coming up. So smart fluorescent organic materials, I call it this as organic materials for chemosensing. So I've given I think it's not a brief, it's not an elaborate, somewhere around in between introduction to all the things what we are doing. So now this is the main design principle. I have told the common principle there, but what we have slightly modified our principle. So we have a fluorophore and ionophore constructed together, and we have a spacer. We had additional ionophore and a fluorophore together. This is what our design. What we have seen before, generally only one design, ionophore and a spacer and a fluorophore. But we put a spacer here, we have one more, so two sides. So both the sides, and then it can easily capture anion or a cation or any other neutral molecules. And then when you pass the fluorescence light, so there is a change. So this we call it as calorimetric and or fluorimetric detection of anions, cations, or neutral molecules. So now this part can be played around, this part can be played around, this part can be played around. So you can just change the groups and check what happens. So this is what design. So this is a typical example of one such molecule, a representative example. So these two are called as fluorophores, pyrene moiety, and these two are called as the ionophores. So these heteroatoms are responsible for binding with the metal atom. These are called as ionophores, and this molecule, so ion binding sites, and this is called as the linker. So this is totally a modular fluorescent chemosensor. So we can change this group into pyridine, this group into anthracene or naphthyl. So whichever that you can just play around with all these things. So this is what we have designed, and the project has been sanctioned for that also. So this is our basic molecule, xylylene dibromide. So xylylene dibromide, we have designed this for a silver sensor, and then we have designed the same pyrene, but here there is no nitrogen, only 4 heteroatoms, but here we have additional one more heteroatom. But because of this heteroatom, this mechanism is different, this mechanism is different. The science behind is different. So this is for mercury sensor, and this is for zinc sensor with the help of pyrene and the bienol group. And then this is for, we have developed for an aluminum sensor. When you change the pyrene to an anthracene, it recognizes aluminum. Similarly, with the same thing, we have taken for naphthalene group, and it senses for iron. And then we have taken the same bienol, but just a CH2OH group. It's a dual sensor. It senses nickel as well as aluminum. And then we have made a chiral sensor for this, but of course the chiral results are unpublished, but it senses for aluminum here. And then this is for cerium sensor, just quinoline based, okay, hydroxyquinoline based, but the major linker is this. We are just keeping this constant and changing the fluorophores and ionophores. And this is for strontium, and this is still unpublished works. So these are all some of the sensors which we have developed in our group so far. So this is what I commit to, that how we do that. So pyrene pyridine conjugate as silver ion selective fluorescent chemosensor. So this is what I told about. Here you can see only 4 heteroatoms, but here we have one more additional heteroatom, though they both recognize silver. They both recognize silver, but the mechanism is different. So this is what its preparation procedure, very simple, but we should have 100% pure sample. So we take pyridine methylamine and then reaction with the styrene aldehyde with sodium borohydride reduction. We get this guy, and this is then coupled with 2,6-bis bromomethyl pyridine for this one, and methylene xylene dibromide, metaxylene dibromide to prepare these. So these two sensors, the only difference is you have a nitrogen additional heteroatom, but here that is not there. So when you take the first one, you can see we have tested for several metal ions: magnesium, zinc, cobalt, iron, nickel, potassium, lithium, etc. But this peak, for silver alone, there is a quenching takes place. So these two are monomer peaks. This is one, two monomeric peaks for pyrene, and this is the excimer. That means these two pyrene comes close together. So in the excited state, they form a dimer, these together. This is one, this is two. They do together to form a dimer. So this is a dimeric. So that's what we call it as excimer peak. So this is the excimer peak, and this is the monomer peak. So what happens, the monomer increases and that is enhances, and the excimer quenches in this case. So this is highly selective only for silver and not for other metals by fluorescence. So you can see here the monomer enhances here, but the excimer quenches. So this is this mechanism here. Okay, monomer enhances and the excimer quenches, and we recognize silver when we compare to the other metals. So these are all the basic calculations, the Jobs plot, the Benesi-Heidelbrand plot to find out the association constants and limit of detection, etc., and some supported by the theoretical by HOMO and LUMO, and it's also supported by the mass spectroscopy. This is the exact peak of the sensor with silver ions. So even the NMR spectroscopy, when you add silver, you can see there is a shift in the protons. That means silver is acting, or it's binding to this sensor molecule. So this is when you introduce another nitrogen. So it's interesting, just only one nitrogen is changed here. So that importance of heteroatom, the mechanism is totally changed. Here it is completely quenching. Okay, so previously these type of mechanisms, we call it as a ratiometric sensing. So you have an isoemissive point here. So this can be converted into quantitative measurements. Okay, when you have a isoemissive point here, because this one is going top and this one is coming down. But in this case, it is only quenching. Even the monomeric and the dimeric, eximeric, both is quenching. There is no isoemissive point, or there is no one enhancement, one quenching, just a change of one nitrogen. So the mechanism, see, entirely it is quenching. So just introduction of one nitrogen, the total mechanism is changing. But luckily, both are for silver. Sometimes we get different, because the problem is the shape and the size of the molecule here, the cavity size. So that plays a major role in the selectivity of metal ions. So that also with the NMR spectrum. So there is a shift in all these things. I don't want to go into all these details for want of time, just I brush up. So this is another important, as I told you, this is called as the interference study, because in your body, there are several other metals. So your sensor is particularly for silver. How do you know? So you have to check for interference studies with other metal ions. So we have checked this. So it is only selective for silver in the presence of other metal ions also. So we have calculated the limit of detection. It is up to 10 power minus 8 molar, and the association constant is 1.6 into 10 power 4. And these are all the other kinetic studies to find out its limit of detection and its association constant, etc. So this is one of the important studies, which we make sure that it is only selective for silver when you have many other metal ions together in your body or in the environment. And this is the sort of theoretical works to calculate the HOMO-LUMO energy, and it all matched with what our evidence we are given from spectroscopic and analytical evidence, and it matches with the theoretical evidence. So what we call this as a monomer and excimer emissions. So these two guys come close together to form excimer. So both monomer and excimer is just like a butterfly. When it gets, because it quenches, so when it is close together, the excimer is more. But when these two guys go far like this, when they go far, the excimer is quenching because of this complexation of silver here. So we call it as a butterfly shaped molecule. Okay, both monomer and excimer quenching takes place. And these are all its SEM images. This is our sensor, and this is with silver. And we have applied this for water treatment. This is one of the applications. So to find out the amount of silver present in the water. So we have taken tap water and wastewater in and around our Karunia campus and see the recovery. It is almost 100% in all the cases. So it can easily determine the amount of silver present in this water. So I'll come to the second thing. This is the same strategy where we have used the linker, metaxylene dibromide, but here this is a phenyl glycinol. L-phenyl glycinol, an amino alcohol, and same pyrene. So this mechanism is a pull fluorophore push ionophore mechanism, but after it binds with aluminum, so these guys push together. That is fluorophore push away, but these two guys pull each other. Which one? These ionophores, but the fluorophores go away. Okay, the fluorophore push, but these two guys push. So we call it as push-pull mechanism here. So this is pyrene phenyl glycinol linked ratiometric fluorescence chemosensor. We followed the same strategy. So phenyl glycinol with pyrene aldehyde and all simple with the sodium borohydride reduction, we get this molecule. And thus again with xylene dibromine, we end up with this. So this is a chiral center, and we have done some chiral recognition, but still they are in unpublished results. So you can see here the previous molecule, this one half of the molecules, there is no selectivity at all. See, no selectivity. We cannot tell this is selective for, because it almost all the peaks are like this. So we need to have particular selectivity for one or two metal ions. But here there is no selectivity. That's what we had our own design with two sides. So see here, it is two monomer emission and excimer quenching for aluminum. All the other metal ions are located here. Always the enhancement process is good in terms of biological applications. Okay, quenching is not so much good. So aluminum sensor, so that's NMR titration, and then IR spectrum, and even COSY NMR spectrum. And then you can see the absorption. Before that, we need to check the absorption spectra to fix the excitation wavelength, as well as to check whether there are hydrogen bonding or any aggregation forming. Everything we have to check with the help of UV. And this is the interference studies. It doesn't interfere with any of the metal ions. It's only particular for aluminum. This is what I told: excimer quenches and monomer enhances. So this is an isoemissive point, so that you can easily use for the quantitative determination of this. And these are all the kinetic studies, and then to calculate. And this is one more important thing, is reversibility. I told the first two approaches, they are reversible sensors. The chemisometer is irreversible. So this is a reversible sensor. So you first put your receptor is here. When you add aluminum, it goes there. And then when you put EDTA to that, the EDTA captures the aluminum, so that again quenching takes place. Again, you add aluminum, it goes down, so that your sensor can be easily washed away by EDTA, and then you can repeatedly use this. We have checked till 20 or 23 cycles for this particular sensor, this reversibility. So reversibility process is always good, because you can reuse that a lot. Or else if it is a dosimeter, it is one-time usage, right? So we have applied for bioimaging studies. So this is what when you have different concentrations of aluminum here, you can see how it glows. So it can be used for biological purposes, also for the detection of chemotherapy. This is the possible mechanism we have talked about, is excimer quenching and monomer enhancement. So the third one I talk about is just the anthracene moiety. So here the only thing is, instead of pyrene, we have changed anthracene, and it also senses aluminum, and we have gone for bacterial, particularly E. coli imaging in this. Okay, so it's a synthesis process, and it's data, NMR, and all those data. And you can see here it is only selective for aluminum. So I just skip off for the want of time. All rest are all the same, and theoretical studies. And this also you can see here, we have applied for water in Karnia Nagar water, and then Selvapuram, Narasipuram, whatever water we have taken, and its efficiency in aluminum detection, and also E. coli cells stains, how it gives glowing. So to detect E. coli, but we are not able to differentiate this E. coli from other bacteria. So we tried for that, but not able to do that. But anyhow, it gives good imaging with E. coli. So this is another one, which is a dual sensor. So it can sense nickel as well as it can sense aluminum. So here, this is the binol-based molecule sensor. It is for chiral recognition purposes, but even it detects the metal ions. So through the internal charge transfer process, it detects aluminum. First, it detects aluminum, and then if you add nickel, the aluminum is displaced and it detects nickel. So nickel is more bound to the receptor than aluminum. So it is a dual type receptor, and its the synthesis is shown here. the same, we are using the same xylene dibromide, and with our binol we have done this. So you can see here it selects aluminum as well as nickel. Nickel is enhancement, aluminum there is a shift here, so there is an internal charge transfer takes place, but this is a blockage of photo-induced electron transfer. PET is blocked and you get a chelation enhanced fluorescence with the help of nickel, and this is for shifting. So the rest are same, the same kinetics and NMR spectra, and this is what the displacement. So first it detects aluminum, and then when you add nickel, aluminum is displaced. And the interesting thing is, because it has two dual sensor, we have taken one as nickel as input 1 and aluminum as input 2, and we have developed a molecular electronics, like what we call molecular electronics. So development of a R gate, so it can be used in as a molecular devices also later on. So we are probing into that detail. So this is what one other applications of this type of sensors. So these are also this is the another one, the same binol molecule with pyrene. Okay, so this is binol with pyrene. So this molecule, so this is particular for zinc. Okay, so you can see here the visual color change when it reacts with zinc. So here also monomer emission and then excimer emissions takes place. So you see here it all enhancements, monomer enhancement taking place, excimer enhancement is also taking place. Previously the excimer was quenching, but here all are enhancing, and you have a isoemissive point. So these type of sensing is called as ratiometric sensing, where you can get quantitative data out of that. So this is one more, the other approach, and chemisometers, we have one such publication with that. So this is a naphthalene-based molecule with a disulfide linkage. So this guy, so this is what the preparation, and this is generally non-fluorescence. So this is what non-fluorescent molecule. But when you add mercury, this guy is cleaved, and you get back this one. So which is, so you can see here, so when you add mercury, the fluorescence is very high. That means this disulfide linkage is cleaved, and this gives you good fluorescence. But this is what chemisometer. Why? Because it can be used only once, and it cannot be repeated again. So this is called as dosimeters. So it is only for mercury here when you have the interference studies, not for all the other metal ions. Only mercury can cleave this, and you get the fluorescence enhancement. So this type is called as dosimeters. Okay, so I still have 5 more minutes. I don't want to talk about all these things. Similarly, all our different mechanisms and different applications. So this is for nickel. So we have the bioimaging for nickel. This is one type of seminar based on, sensor based on the chalcone molecule. These are all several other chalcone molecules, like anthracene-based chalcone molecules for lead sensor. So this and this. And then we have even done graphene. So these smart materials these days, we have taken graphene, and then we have put resorcinol, and we have used as a cerium sensor for all these things. So cerium nitrate, so cerium sensor recently, these are called what we call it as smart 2D materials also. So my conclusion is, using the supramolecular chemistry principles and following the green chemistry protocols, several chemosensors can be developed for varied applications like cancer theranostics, and in the following areas: in water and environmental monitoring, sensing and removal of toxic metal ions, or safety of food, rapid detection of metal ion contamination, or healthcare and chelating drugs in biosensors and metal ions. And as I told, in the applications for explosives, for bacterial, for fungal, and all these areas, these chemosensors can be used. So based on this knowledge, what I always tell this, the take-home message for this seminar is: watch the society, you catch the problem, apply your knowledge, whatever science knowledge you have, you supply a solution, but make sure without the pollution. And this is our Karunya campus, which is located at the foothills of the Western Ghats. And this is our International Prayer Center, Bethesda. And this is our road to Sirwani Dam here. And these are all the hostel campuses. And we are located in this building, our chemistry department. This year, you're always welcome to come to university and visit our labs. And this is our main building, and we have all facilities. We have recently installed the 300 megahertz NMR also, and we have IR, fluorescence, UV, HPLC mass, GC, and then XRD, and then SEM and PLD, etc. So you are always welcome to visit our university for any sort of collaborations, etc. So this is my research group. I need to acknowledge my students. They are all in different parts. This guy completed his PhD. He's working in Dubai. These are all, this guy is working in SRM. These two guys are working in SRM. This girl left to Czech for PhD, Czechoslovakia. And this girl is doing PhD at Karunia itself. And this guy also went to Czechoslovakia for his PhD. This guy went to Taiwan for his PhD, Pandya Rajan. These are all nanoscience students. And this is Dr. Velmurugan, who did most of this work, and now he's working as a PDF in China and Zhejiang University for the past 3-4 years. And I wish to acknowledge the DST for the fast track and EMR support, and Karunia University for providing the space and other infrastructure, and SAIF Punjab, IIT Chennai for spectroscopy studies, and all my collaborators for theoretical and all those things. Thank you. So your comments, suggestion, queries, please. And this is my address and my mobile number, and my email ID is this place. Thank you once again for the management, for the HOD, for providing me this excellent opportunity. Hope I am on time.
Participants can post their questions in the chat box. Participants, kindly post your questions in the chat box. Sir, there is a question from Sriram Prabha ma'am. I'm working on graphene. I'm working on graphene and conducting polymers. I use them for environmental pollutants like
Environmental?
pollutants. I use them for environmental pollutants like cadmium and healthcare copper. My question is how I can choose solvents for these optical studies.
Balakumar
Yes,
is
ma'am.
director.
What I need to know is they are working on graphene means what? What is the other material for which they have made the composites? Because as I told you, those mechanisms in nanotechnology based nanocomposites, the mechanisms have not been explored much. So what type of material they are using? Based on that, whether the detection of cadmium can be happening or not, we could know. But just if you take graphene and graphene oxide or reduced graphene oxide and you don't get any information out of it. So what is the other molecules they are adding? Any nanomaterials or any organic materials or inorganic materials, what they add? Based on that, we could get some information. I need to know that to talk about more on that.
Tin oxide and graphene, sir.
Yeah, tin oxide and graphene. So basically I told the shape and size matters. So what type of shape you take, that tin oxide nanomaterial, what type of shape? These days we have a tadpole shaped molecule, we have a ladder shaped molecule. So the shape and the size of the molecule plays a major role. So we have to check and tell after using your UV
sir, it's
and
spherical
fluorescence.
in shape, sir. Spherical in shape.
Yeah, that's what. Okay, that's fine. So that spherical shape, and what is its coordinated, I mean, what is its role with the graphene? Whether it is physically absorbed, chemically absorbed, and all those things coming together, we can talk about the mechanism. And the $1 million question here is, even me too trying, we cannot specifically design a sensor for a particular metal ion. Based on my experience, if you have these type of heteroatoms, it will sense like that. So that's all we can do. But you cannot define a sensor except chemisometer. Chemisometer you can design because chemical reactions takes place. But all the other things, with the help of a knowledge, if you have these molecules, it can sense these group of metals. Like that only, we cannot design particularly for this metal. It's only based on these designs. So we have to check with the help of fluorescence and UV and check what it can detect.
Thank you, sir. There is another question from Pavitra. So you talked about the upconversion process. I wanted to know whether the anti-stroke emission can occur in the blue region itself, or it is possible for a molecule.
Yeah, of course. Yeah, it is possible based on tuning the fluorophores.
Whether it's possible for a molecule to excite and emit at the same wavelength.
Generally not possible, but I'm not sure about the nano area. But in organic molecules, generally it is not so possible.
Thank you, sir. Thank you, sir, for your galvanizing time with our participants.
Thank you.
Great is the art of beginning. Greater is the art of ending. We have been listening to eminent speakers deliberating on the breakthroughs and approaches in contemporary scientific research. All these effectual insights gave us a new perspective and a wholesome learning experience in these 3 days. We hope you all had a useful time in traveling with us in this conference. After remarkable, thought provoking 5 technical sessions, we are here at the valedictory ceremony of our conference. May I now request Dr. S. Nirmala, Principal, PSGR Krishnamal College for Women, to welcome the gathering and introduce our speaker, Professor S. Balakumar sir, for the valedictory session.
Thank you. A very good afternoon to one and all who are connected virtually with us for this 3-day International Interdisciplinary Virtual Conference on Breakthroughs and Approaches in Contemporary Scientific Research, organized by the PG and Research Departments of Chemistry and Physics of our college. And this program is done in collaboration with the Departments of Physics and Chemistry of University of Dar es Salaam, Tanzania. I'm very happy that we have come to the final session of this 3-day international conference, and it gives me immense pleasure to welcome you all for this final session. And I extend a very warm welcome to Professor S. Balakumar, Director, National Center for Nanoscience and Nanotechnology, University of Madras, who is here with us as the chief guest of this final session. Professor Balakumar has received his PhD in Faculty of Science from Anna University, India, and he has acquired his postdoctoral fellows from the Chinese University of Hong Kong and National University of Singapore. His field of research includes nanostructured materials for energy, environment, and biomedical applications. He started his career as Senior Research Engineer in Chartered Semiconductor Manufacturing Limited, Singapore, and later continued as Senior Scientist at A-Star Institute of Microelectronics, and further moved to NCNSNT, University of Madras. He was also serving as Adjunct Associate Professor at Department of Mechanical Engineering, National University of Singapore. The SAR has more than 250 publications in peer-reviewed journals and more than 8 US patents to his credit. The professor has published several book chapters and edited several books and organized more than 40 international and national conferences, workshops, seminars, short-term courses for the past 12 years. And he's also the associate editor of Chemical Papers Journals, a Springer Journal, and serving as in the editorial board member of various other journals. 20 funded projects from various funding agencies, several awards including TANSA 2018 Senior Scientist Award from TNHE are added to the feathers to his cap. I'm immensely pleased to invite such an eminent person to be part of our international conference and deliver the valedictory address and share his expertise with the participants of the conference. Let me also take this opportunity to congratulate the institutions involved in this conference. From our institution side, the Department of Chemistry and Physics and the UDSM for completing this conference with phenomenal lectures being delivered by prominent speakers. So my appreciation and congratulations goes to all the organizers and the persons involved in this conference. And I wish that we have many more such programs in collaboration like this in future, which will benefit larger group of stakeholders. I wish all of you good luck. Thank you.
Thank you, ma'am. May I now request Professor S. Balakumar sir to address our esteemed audience.
Yeah, very good afternoon to one and all. At the outset, I thank our beloved principal for the very nice introduction And also I thank the organizer for inviting me to deliver the valedictory address on the topic of biomaterials and application. And and it's really a great pleasure for me. So can you allow me to share my slide? Yeah.
Sir, you can start sharing your screen, sir.
Right. Yeah, the topic of my valedictory lecture is biomaterials and their applications. So generally, there are biomaterials are used for various application, basically for drug delivery and support our system. So here in my lecture, I'm going to cover for next 30 minutes regarding the materials that used to support our heart tissues. So that materials are generally, I mean, the outline of the lecture goes this way. So quick introduction about functional materials, and then one of the specific materials that we are working on, bioactive glasses, and what kind of application that we are using for regenerative and orthopedic and ophthalmology. Depend upon the timing, we can cover this topic and this in this valedictory address. And it's really a wonderful opportunity. For the past 3 days, I think you have learned a lot. And this is completely on the biomaterial. So the biomaterials are also a class of a functional material. So the functional materials are also have a lot of application. Let's start with the definition. So there are many materials are used in the past, which is called inert material, and then later the materials is for responding when you give a certain external stimuli, which is called as functional material. And also when you change the size of the material and materials become smart. So we also call it as a nano material, and it also respond to more than one external stimuli, or you are giving one external stimuli and there is a change in another property, which we call as multifunctional material or a functional materials, and then subsequently we say multifunctional material. For example, I think I can take two examples to explain what is functional material. One is the photochromic and photoluminescence glasses. So generally we are using some of the glasses, spectacles, it changes the color depend upon the light. So sometimes it is a dark if it is a bright, and if it is it's a colorless, it will become a dark. So this basically is a coating on the glass. The materials coated on the glass respond to the light. So it is called as a functional materials, also called the photochromic glasses. That is also used in the aeroplane windows and the vehicle windows. And similarly, there is another example is the newspaper that is demonstrated long back in Harvard. So they did some coating on the paper on a paper. So in order they also use as a newspaper. They are not changing the coating. They are only changing the content. But with the help of the electronic materials coating, they use this called an electronic paper. And similarly, there are such materials are used in the for automobile industry, for vehicle industry, and also they are basically in the piezoelectric and electrostatic ceramics, and also they used for NIMS and MEMS application. So these are all called functional materials. So when you say the functional material or multifunctional material, and we are using the nano material, generally when you all know the nano material reduce the size, the properties are changes significantly as compared to bulk. But when you connect this material to nano material to the macro world as one of the long-standing effort in the nanotechnology. But it's remain a big challenge as it needs further understanding of the system. When you want to understand this material, you have to understand the material down to the level of atom. For example, starting from the preparation to have a better control on the structure and the function of the either the nanomaterial or bulk nanomaterial. The role of size and the shape, architecture, composition, and nanostructure need to be systematically investigated, and each and every nanoscale material, and then you can integrate, you can make a composite. For example, the picture in the slide, it shows that the material is an animal with a 3 different face. That means that if the material if you rightly synthesize and rightly use a right shape and architecture, and you form a composite material, it certainly become a more powerful and have a n number of functionality. So that is what our end goal or the final goal as a material scientist. But when you want to use this for certain application, you can customize it and you can make it more functional and more effective with the help of nanostructured material. There are, I think you might be attended many lectures during this conference on the nanomaterial. I'm not going to explain that. I just want to give a one point here: design and synthesis. So design and synthesis is based on the customized requirement. For example, you can, when you say that I want to increase the functionality, you cannot make an alloy or a compound all the time. You have to make a composite material. And so based on your requirement, for example, when you want a material required for optical property or magnetic property or electrochemical property or magnetic amplitude, you can use an either chemical interaction or electrostatic interaction. You can combine many different material so that it may be a more of a functional material. So depend on your requirement, you can synthesize. So that is called the design and the synthesis, which is called as a nanostructuring with a defined property. Obviously, there are quite a lot of topics are there. Nano assemblies and nano hybrid and materials are being used. So, but in our lab, one of the area what we are working is in biomaterial. Just quickly, I just want to one side to consolidate what we have done so far for the past 7-8 years. We are working on one of the biomaterial which is called as bioactive material. It is one of the calcium phosphate compound. So that we have synthesized using, it's actually we synthesized using nanobioglass. I mean in the form of nanobioglass. The glass means we are using silica matrix. Silica is a nano where we can add calcium and the phosphate and the sodium, and we will form a different compound in the network. So we have systematically synthesized and we varied the structure of the material, and we made a composite with a TiO2, PMO, RGO, and integrated with HAP and the PMMA. And then we move to the next level where we make a product for industry as well as for our ophthalmology application and also for orthopedic application. So recently we also developed one product with the help of Birac, where you can use tooth socket fit hemostat. This is when you work on a material, you work on a certain period for to understand the material, to make the material to useful to make some composite and customize the material. Then you can move on the product. So this is our roadmap, what we have done, and we are going to we are working on it, and towards for other products, for example, with the hemostat, for also for a 3D printing. So this is our roadmap for this. So, but initially, so from the beginning, what we started with a biofunctional material. We discussed what is functional, what is multifunctional. Now we can see what is biofunctional. So, since more of the participants are students, I just want to start with the biomaterial. So, if you look at the picture here, we are using there are many material inside the body to support our bone, to support our knee, to support our hip, or maybe for face makers, for eye implantation, for cardiovascular implant, and then shoulder prosthesis and dental implants. So there are many different materials are used from the beginning. That you can also define and classify it. So what is biomaterial? Biomaterials are non-living material used in the medical device or inside the body to design and interact with our biological system. But how do you classify it? Whatever the material that, for example, used when you have problem with your bone, we are using a material which is maybe titanium alloy or some other metal alloy material, which do not trigger any reaction in the host, neither rejected nor recognition. So, but do not bring any good result. Maybe you have a lot of, because it is when you put this material in your body, it is an enemy to the body. Your system will reject it. But later stage, they also coated with certain material to establish the interface between your body and the material. So that material, we call it as a bioactive material. Later, they are using a material, or we are using the material. This material can be a strong material, but later it can be biodegradable. So it is called biodegradable, biocompatible material, or we can say smart materials or innovative materials. So there are, even it is moving to the 4th generation, you can customize and you can fabricate using 3D printing. So this is the classification or how the materials are moved from inert to a 3D printing where you are using for various applications. So, but if you take that material, for example, you take a calcium phosphate. Calcium phosphate exists in the form of hydroxyapatite, also bioglass, triglycine phosphate, and also they can also fabricate in a pellet form, also fiber form, also in a putty form. And then these materials also can be, as I said, it can be coated on the implant material to establish an interaction between the material and the body. And also it can also be used for that also can be used in the bulk material in a nano structure with the bulk. It can be used as an implant material. And similarly, this material can be used for targeted drug delivery and also for diagnostic and imaging, and also for cancer therapy, for hyperthermia, skin cancers, and the gene therapy. So, and also you can attach many growth factor. So when you use it for this one, so there are plenty of application. And when you move from the material biomaterial to a nano material, so that become a nano biomaterial. But we have to understand certain, I just narrow down for next 20 minutes to understand why we need, how you can, what kind of material we can use it for our bone and teeth, and what is the, what is a close relation. For example, if you take a bone is, this is the left side of the bone structure, and if you get inside, you can see the fibril structure. The fibril structure, if you further you look into down, you can say a collagen fibril. The collagen fibril, if you do it, it has a microfibril and bioapatite. The bioapatite is in the form of crystalline material, which are nanocrystal, which are hydroxyapatite. Similarly, your teeth also have a same material, is a composite. Bone and teeth also basically a natural composite inside the body. They are certain percentage, it is a collagen. Collagen is in the bone. Collagen is in the bone, whereas you have a different other polymers here. So our tooth is such a beautiful structure. You have a dentin, you have a pulp, you have a enamel, but all of them are having calcium and organic. But you have to one of the very interesting fact is that enamel is the strongest portion in our body, which has a 95% of calcium phosphate, and the remaining it is organic. But there is a gradient among the dentin, pulp, gingiva, and alveolar region. But more of this there you require, when there is a problem with the bone or problem with the knee, you need a synthetic calcium phosphate with a very good with a nanostructure or a hierarchical nanostructure, you can, so that you can repair or regenerate or reconstruct these hard tissues, which are called as bio-nano materials or bio-nanotechnology, right? This is one of the area. And again, this slide will show you the composition of the bone. The composition of the bone, as I said, hydroxyapatite is a 60%, 25% is an organic material, 50% is a water. But whereas tooth structure, as I mentioned, it has an alveolar bone, cementum, pedial membrane, and gingiva, and dentin, and the enamel. I think whenever you go to a dentist, they will tell you, oh, your enamel gone, or you have a problem with that because of maybe dental caries, maybe for other issues. But you have to understand that as a material scientist or a physicist or a chemist is made up of crystalline nano material, right? Then, But when you say hydroxyapatite is one of the very good material, which is as I said, we have given the formula where the calcium phosphate ratio is 1.68. We all know when you see the advertisement in the TV, they are saying that fluoride rich or other material rich toothpaste to enhance the property, or to protect your teeth. So there are many different names for this material. It can be a biological upside, it can be of fluoroapatite or chloroapatite, and they are but they are in the nano form. This is one of the material in the crystalline form. But this material, when you see the synthetic material, it is not new. It is not new. Already exists in the market in the micro form. It can be calcium hydroxide apatite, or it is a TCP, and it is exists in the gel form, and it is a pellet form, and also in a paste form, and there are many forms exist. Or if you have any problem with your ortho, your bone, doctor prescribe these kind of things for filling and also as a tablet. So, but you can see where we can use it. Use it. As I mentioned, you can also use it for the ligament tear, and also for you can also design for your hip bone, and also for you have a problem with for harvester hip bone, for bone harvester, and also you can use it for bone defects. So these are the areas we can. So what we have used in our lab. So it is not whatever they have done. Quite a lot of work has been done. What we have done is we synthesize material. We want to improve the mechanical property. There we use high temperature oxide and integrate with material. We improved the mechanical property. Similarly, we all know carbon graphene is one of the very strong material. But pure graphene may not be required because hydroxyapatite also had a lot of oxidation. So we used to reduce the graphene oxide and the graphene oxide. There we improve the mechanical property. In order to increase the cell activity, osteoblast cell activity, or use this material for both osteosarcoma, that means bone cancer, we have also designed and developed an ion incorporated non-oxide apatite, and we systematically evaluated. There's another one, but for when you form a material for scaffold, what we have done is the scaffold can be biodegradable, and it can be a spongy nature because you cannot exactly fit for a where you have a bone defect. So spongy kind of thing, you can squeeze and fit it inside. So it has to be mixed with the polymer. So where you can use a PMMA or PLGA or PCL, and then we combine with the nano hair, we able to make a porous. It is a scaffolds. And then now we move to from here, this all freeze drying method, we move to a 3D method that there are many techniques that we are using. Similarly with sulfate, which we have made, and also that kind for bone substitution. This is one of the. But however, this material also have a lack of certain mechanical strength still. So what we are doing is, and also the degradation and biodegradability is not easy because it is highly crystalline, very strong material. So in order to avoid that, in order to substitute that, Professor Henge has developed a material which is called the bioglass. Bioglass, as I mentioned earlier, you have a silicon dioxide, and as a matrix where he can incorporate sodium, calcium, P2O5, and he demonstrated two different compositions with the 45% silica and 86% silica, because one material is a bind with the bone and tissue, whereas other one, which is not bound to the soft tissue, is not facilitated. So, but that is an initial, that is basically an invention. But after that, quite a lot of modification and engineering were done. So in that sense, or in that direction, so we also made quite a lot of work towards a dentistry to address to develop the material for hemostat. That means hemostat means basically when you remove your teeth, normally it filled with quite a lot of build within a few seconds. But if you can develop the hemostat using a calcium phosphate, and if you insert it, definitely it will arrest the blood, and also it will preserve the structure. And similarly, there are many implants are being used, but coating a bioglass establishes the interface between your shaft and the hard tissues. And also there is one of the critical is in the PDL membrane, periodontal ligamental membrane. Replacing or repairing the membrane is not easy. So HAP waste may not be ideal material. So bioglass is an ideal material. What we have developed is this one. This is one. Similarly, this can be used for various purposes. For when you develop a right composite, it can be used for bone grafts and scaffold and bone cancers. So it is, as I mentioned, this calcium phosphate also exists in many different forms. In a nano form or mesoporous and hydrogel and bone fillers and for drug delivery vehicle and hyperthermia. It is a plenty of application and there's a lot of openings for this material. But what we have done is we moved the platform from micro to nano. When you say micro to nano, as I think you have seen already, when you increase your surface area, the interaction is more. The interaction is more. It can easily establish the interaction with the mode. So that means it can easily convert from convert. So that is what it happened. So that is case. If you look at this material, this is such a wonderful material, and it can be used not only for dental and ortho. It also can be used for drug delivery and also for ophthalmology application. So when this is also commercially available in putty form and also in injectable form and template form, and also used in for bone graft and filler in micro form. And another important fact is that as a Novamin, which is also used in Sensodyne. I think most of us, all of us, we know that Sensodyne is prescribed for those who have a sensitivity issue. The sensitivity issue means you lost an enamel. Enamel is an irreversible. Once you lost it, that's it. So only you can grow a protective layer. Sensodyne is the one which you can promote the growth of promote a layer on top of on the dentin tubule so that it can close and you can preserve your teeth. So that is one. So, but what is the help of nano? When you say that these are all so far what we have discussed, they use nano form, microform. But when nano, when you take a protein absorption and if it is a microform, the cell proliferation and cell addition, cell proliferation, cell differentiation is not many. But whereas, as I mentioned earlier, with the nanoscale, this addition, proliferation, differentiation significantly enhanced if you use the right size with the right surface area very close to the bone so that it is biocompatible. Adhesion percentage increased to 24%, stimulate the surface topography of physiological pore, such as a major advantage. But because of that, in order to understand the material thoroughly, we have developed a material with a spherical structure, fiber mat, flakes, core shell, nano seeds, cubes, hollow fibers and rods and platelets and sheets, tendrimer. So actually in our lab, or what we have is whatever the chemistry we choose, we used all sort of different wet chemical method. We try to understand the role of the shape and the architecture. So that means we take one chemistry and fabricate in many shapes. So we have developed many different form. So it is not only spherical, you can see hexagonal structures and platelets and rods differences. So these are we have developed well with that. Then we have just for sake of understanding. So when you want to develop a material with a wet chemical method, right after the preparation and before go for annealing, normally we used to do the TG analysis to see the weight loss. When there is weight loss, in turn will give you the onset of the phase formation. So once you get that number, you can anneal at a different temperature. That will give you many different morphology. In this case, if you look at it, TGI is around data, it is giving 750, and after that we have been annealing at 600 and 750 and 800. You can see the morphologies are different. Morphologies are different and the sizes are different. Surface area is different. The structures are different. So that it will also you can see that the hemolysis is one of the biocompatibility study with the human blood, where you can see that when they put the material with blood with a certain chemical, it has to, the sizes of the microparticle in the blood start, but if it is below 0.3, we can say it's a biocompatible. But we can see the material prepared at different temperature, we have different morphology as a different hemolysis. And also that is, we found all the three materials are compatible, but the 800 material is less compatible with the other two material. We also use the fibroblast cell line to see the biocompatibility with the cell line. Is a cell proliferation occurs after 28 hours or 48 hours. We show that there is a growth of structure with the with respect to the it shows that. So it is all these structures are stable, but relatively 600, 800, the material is highly biocompatible. And similarly, we also use different sonication process or annealing process, which give a different morphology. When the morphologies are different, surface area is different. You can see that the normal method give you 20 centimeter cube by gram, but whereas when you use a microwave annealing, it changes surface area. But when you introduce a probe sonication, there is a break in the particle size, and that changes the surface area, porosity increases. That certainly increases the property, but that metals are good for hemostat application. So that is one of the work. So similarly, as I mentioned, I'm just skipping this slide because I will talk about this one. We are trying this material for dentistry. The defects are, the dentistry, one of the major issue is the dental caries. It is one of the fifth prevalent chronic diseases. So it can damage your teeth, and once you can lose your teeth. But if wherever the water has a strontium, there they have a less dental caries. That is our big data analysis or data science says that there are, wherever the water in the world we have a strontium, the people have a less number of caries. So strontium is one of the good material to integrate or to add with the biomaterial to resolve the dental caries issue. So what we have done is we used the sol gel technology, and we found a high strontium content bioglass. Then we worked with one of the local hospital, Ramachandra Medical Hospital. Then we taken the donor's teeth, we polished that, we exposed the dentin tubules. Then we brushed with our material developed. Within 5 days, we found that the dentin tubules are closed even with the 5% of strontium, and it improved the 10% of strontium. And another important point in bioglass is one of the very good antibacterial material. So inside the tubule, whatever the infection, it is remove the infection, and the dental tubules are closed, and we have able to grow a very thin layer on top of the enamel. That has recently published in our Journal of Material Science. Subsequently, we also developed the hydrogels for various application. But when you say hydrogel, certainly it is a composite. Whatever the material developed with the bioglass, then we use natural polymer, synthetic polymer. We make a hydrogel for drug delivery, and make tissue. We did tissue engineering and also hemostat. So that is these are one of the strong area where we are working. What we have done is, with the developed material with the sodium alginate, we made a hydrogel, and then we made a lyophilized thin sheet, which we called as a membrane. That membrane is also can be used for many different application. We have this can be used as a hemostat and used for dental tissue engineering. Similarly, we also developed a bioglass material to arrest the blood. So that is material we also here we have got the hemostat data. So that is called the thrombosity and absorption. We have shown that and systematically evaluated it. You can see that this when the material prepared with a 800 temperature, your hemostat properties are very good, and it immediately arrests the lyses it and arrest it. So this is one of the material what we have developed. And again we can with the alginate and bioglass ceramics, we also did different co-culture studies. We can take an epithelial cell, and also with an osteoblast cell line, because our body doesn't have only one type of cell. In particularly, you have in the teeth, you have two to three different types. So when you have a membrane, we have to see that how the cells are proliferating. So making one cell proliferation is very easy, but when you put two cells, the spheroid form of structure and the subsequent tissue formation is an important. That we have recently demonstrated and we found within 7 days such a cell co-culture also occurs. That is also improved further with the zirconium content that improve the mechanical property, also epithelial cell proliferation. Another important aspect is that, many of us, when you remove the teeth and within a short period, your tooth structure or your extraction socket will undergo a resorption and remodeling of alveolar crust occurs. But if you want to replace with certain artificial teeth, you have to preserve the structure. So recently we found we developed a product. That product can be designed and fabricate, and once you remove the teeth, it will completely filled with bed. Then you put your hemostat here. What will happen is it will preserve the structure, and it will regenerate the tissues from the bottom. That is one of the area which is socket fit hemostat. We develop whatever the material we developed with the beads, and later we also worked with the SRM Dental College, where you can work with the doctors and you make a tooth socket, and we fabricated tooth-shaped hemostat. That is called socket fit hemostat. This is one of our small achievements from our past 10 years work, and 10 years work. So, and later we also looking for a dentin remineralization. Dentin remineralization can be promoted with the calcium fluoride. So the fluoride-rich bioglass we have fabricated using different technique and the structural properties and hardness and hemocompatibility and cell compatibility and antibacterial systematically we established. And later we used this material, and also we evaluated the calcium phosphate content and also the mechanical property. We found it is highly suitable for them. Then we take a tooth from the donors, that is from SRM Dental Hospital. Then we polished the tooth. Then we attached this material and kept it for a few days. We see whether this tooth is growing or remineralization occurs. So that remineralization experiment showed that for example, this is the enamel structure, this is a dentin where we attach the bioglass. When we attach the bioglass, after some time, mineralization this junction is, you can see there is a growth. But the systematic analysis found that your bioglass converted into HCl, that is the natural hydroxyapatite layer, that is demonstrated. Now it is being published in one of the American Chemical Society journal. Similarly, we also established the tooth filling material using this. So copper-based bioglass we have synthesized, and also we worked with SRM Dental. Then we used this as a filling material, and we evaluated using your dyes, and we found that leakage is very, very low. This material is better than commercially available material. This used as a sealant material, and whereas the dye penetration is very less. So another area for next 5 minutes I'm going to discuss is a bioactive composite for ophthalmology. The same material, if you use a right composition, this can be used for corneal application. So corneal application, we know that it is a corneal, that this is a scaffold we have prepared with the polymer bioglass with 53% of silica and the PVA composite for ultraviolet corneal application. First thing is this material should not degrade, and the second thing is transparency should be equal to our equal. So we have fabricated this material, and we with the help of a small mold we made a corneal membrane with a different thickness. This is a giant project with the Shankar Nethralaya Hospital, and we achieved the transmittance up to 88%, and different compositions are made. And later our Shankar Nethraya collaborator, the Professor Dr. Krishna Kumar, he studied the cell compatibility, cell viability using epithelial cells, and also they studied the mineralization in the saliva, not saliva, in the eye liquid. Then it shows that this material is highly compatible. So now we are moving to the next level of bulk manufacturing with a different thickness. This can be also with porosity, without porosity, because it can be used for drug delivery vehicle and also can be used for corneal membrane replacement. So that's all. So there are, these materials can be further explored, can be used for many different applications, can be used as a drug delivery and used for hyperthermia cancer. And there are many avenues when you use a nanostructured material. And apart from that, these materials also can be, once you develop the material, this can be go for 3D printing. So that 3D printing can you can make a design and fabricate the parts that are required. So we are moving to this direction. So with this, I thank the organizer, and this is a list of the publication that we published for the past 5 years. And I also thank the external collaborators, Ramachandra Medical University and Shankar Nethraya, and also for SRM Dental, and also the huge funding we received from Biotechnology Department of Biotechnology, Ministry of India, to support this work. And with this, I thank you, the organizers, and also particularly Bala Vijayalakshmi and the HOD of the Physics Department, and also the principal, Dr. Professor Nirmala, for giving me the opportunities. And with this, I wish you all the best. And also, I congratulate the organizers for successfully conducting such a wonderful, collaborative, and international program. And if there is any question from my talk, I will be very happy to answer. And thank you very much.
Participants can post your questions in the chat box. Participants are requested to post their questions in the chat box. Thank you, sir. The lecture on Nano have enriched us with the ideas of bulk.
Yeah.
We are excited to know how the intellectual waves on these 3 days propagated your mind. Interested participants can come forward with your valuable feedback.
Good afternoon, all. Myself, Dr. Jnanapriya. I'm working as an assistant professor in Department of Chemistry, Sri Ramakrishna College of Arts and Science and Coimbatore. First, I would like to thank all the organizers for organizing a wonderful conference, international conference during this pandemic time. Actually, we got all the updations regarding the nanoscience field and in multidisciplinary aspect. That is the main thing right now we need to be multidisciplinary aspect. And all the sessions were handled very nicely, and we got many contacts with eminent speakers. So I once again thank all the organizers for giving wonderful opportunity. Thank you.
Good morning,
Thank
one
you,
and
ma'am.
all. Good morning, one and all. I am Dr. Shakuntala, Associate Professor of Physics, Sri Vasavi College, Erode. This International Interdisciplinary Virtual Conference on Breakthroughs and Approaches in Contemporary Scientific Research was well organized, and the time management was very good. It was well planned. Messages were updated to the participants where and when needed. The conference was very useful, not only to the students and organizers. It was very helpful and informative even to the faculty like us to refresh our knowledge and we are known to the new techniques and technology through various programs, and the conference covered various areas of current research. Even though the conference was organized by physics and chemistry, apart from physics and chemistry, it covered various areas like biomaterials, environmental pollution, drug designing and pharmacology, etc. Really, it was very helpful, sir. It is very informative and interesting. I thank, on behalf of the participants, I thank the organizers. Thank you very much.
Thank you, ma'am. Now it's time to announce the best oral and poster presentations of all the sessions held for the past 2 days. I request the organizing secretary, Dr. N. Muthulakshmi Andal, Assistant Professor, Department of Chemistry, PSGR Krishnamal College for Women, to declare the results. I request the organizing secretary, Dr. N. Muthulakshmi Andal, Assistant Professor, Department of Chemistry, PSGR Krishnamal College for Women, to declare the results.
Yes, thank you, Silvadharani. A warm afternoon to one and all connected over here. I am much happy to announce the results over here now. On 17th February, we had oral sessions, 2 parallel oral sessions. The first prize goes to Mr. V. Kavin Kumar, Research Scholar, Department of Chemistry, UCE, BIT Campus, Anna University, Trichy. The title of the paper is Fabrication of Bismuth Tungstate Silver Plasmonic Hybrids, Photocatalytic and Electrochemical Performance. The second best oral goes to Mr. J. Harikrishnan, Research Scholar, Department of Chemistry, Annamalai University, Annamalai Nagar, Chidambaram. This was presented in Google link, parallel Google link. The title of the paper is Synthesis, Characterization and Molecular Docking Studies against Anti-Cancer, Anti-Diabetic and COVID-19 proteins of novel 2,4,6 tri-substituted pyrimidines. The same day, the best poster presentation goes to Dr. A. Kalpana, Assistant Professor, Department of Chemistry, Sri Sharada College for Women, Salem. The title of the paper is In Silico Analysis of Antimicrobial Efficacy of Some Natural Products. On the second day, that is 18th February, the first oral Zoom link presentation, best paper goes to Dr. S. Nirmala Devi, Assistant Professor, Department of Chemistry, Kongu Engineering College, Perundurai, Erode. The topic is a study on removal of basic red 29 from aqueous solutions using biochar as adsorbent. On 18th, through Google link, the best oral presentation selected was Dr. P. Saguntala, Assistant Professor, the Department of Physics, Sri Vasavi College, Erode. The title is Biological Applications of Crystals. Again, the best oral goes to Mr. K.S. Kiran, Research Scholar, Department of Physics, deemed to be University, Bengaluru, Karnataka. The title is Crystal and Molecular Docking Studies of bis cyclohexyl diols with focal adhesion kinase inhibitors. The oral Google link presentation, the best paper goes to Ms. S. Hasina S. Assistant Professor, Department of Physics, Mutayammal Memorial College of Arts and Science, Rasipuram, Namakkal. The title of the presentation is Investigations on Photocatalytic Activity of Biotreated Alpha Ferric Oxide Nanoparticles using Phyllanthus neruni and Moringa stinopetala leaf extract against methylene blue and phenol molecules, kinetic mechanism and stability. The best poster goes to Ms. P. Kalpana, Research Scholar, Department of Chemistry, Sri Sharada College for Women, Salem. The title is Global Reactivity Descriptors of Capillin and its Analogues with Cation pi complexes, a DFT exploration. Again, the best poster for the evening session goes to Dr. Rafiq Mullah, postdoctoral fellow, research fellow, Energy Safety Research Institute, Swansea University, Swansea, United Kingdom. The title of the presentation is a low cost and easy operational tool to measure the Seebeck coefficient. A very big congratulations to all the winners and hearty wishes to all the participants. Thank you.
Thank you, ma'am. Congratulations to all the awardees.
Nothing great will be achieved without great human, and human are only great if they are determined to do so. The 3 days went super quickly, immersing in the ocean of wisdom. Let's look back at it as a brief report of the event. May I now request Dr. N. Muthulakshmi Andal, Organizing Secretary, to summarize the conference events.
A very good afternoon to all. PG and research departments of chemistry and physics have organized a 3-day international conference, interdisciplinary virtual conference on breakthroughs and approaches in contemporary scientific research in collaboration with departments of chemistry and physics, University of Dar es Salaam, Tanzania, from 17th to 19th February 2021. During the inaugural session, Dr. R. Nandini, Chairperson, PSGR Krishnamal College for Women, welcomed the chief guest and the August gathering and released the conference souvenir. Professor Thomas J. Limo, Principal, College of Natural and Applied Sciences, University of Dar es Salaam, offered his felicitations and rated the conference a great success. Professor K.C.F. Kilulia, Senior Lecturer and Head, Department of Chemistry, UDSM, declared his views about the conference, highlighting the broad aim and perspectives of scientific researchers. Professor Muthupandian Ashok Kumar, Assistant Deputy Vice Chancellor, International University of Melbourne, Australia, delivered the inaugural address and fascinated the audience about the fundamental aspects of ultrasonics and sonochemistry, the application in nano and biofunctional materials. Dr. P. Meena, Associate Professor and Head, Department of Physics, PSGR Krishnamal College for Women, proposed the vote of thanks. The technical session 1 on the 17th February geared up with an insightful lecture on ionic liquids as environmental benign solvents for sustainable developments in chemical and technological applications by Professor R.L. Gargas, Department of Chemistry, Indian Institute of Technology, Madras, Chennai. In his talk, Dr. Gargas elaborated on the thermophysical properties of ionic liquids and described about the current research trends of ionic liquids as green solvents for chemical and technological industries. Post-lunch technical session of day 1 consisted of 2 invited talks. Professor Nuru Milyuka, Senior Lecturer and Head, Department of Physics, University of Dar es Salaam, delivered his lecture on thin film technology, wherein he explained about the methods of vacuum thermal evaporation and direct current radio frequency magnetron sputtering utilized for deposition of thin films. Dr. Grace Angsker Kinunda, Senior Lecturer, Department of Chemistry, University of Dar es Salaam, articulated an interesting talk on the extraction methods of cashew nut shells and application of its liquid extract as biorenewable material. Madam expressed that these materials, when subjected to different modifications, serve as agro wastes rich in the development of valuable and functional products. Technical session 3 on 18th February started with the invited talk delivered by Professor K.C.F. Kilulia on blue-green algal blooms and their toxins as emerging contaminants in environmental water. In his lecture, Professor detailed regarding the nature of blue-green algae as massive pollutants in freshwater bodies with their specific growth conditions and toxic eutrophication. The second lecture of technical session 3, delivered by Dr. Litiko Mikiusa, Lecturer, Department of Physics, University of Dar es Salaam, who debated on the culprit causing the deficit of open circuit voltage in testerized solar cells and also reviewed on different alloying strategies. Post-lunch session of day 2 included 2 lectures. Dr. Vijay Shankar Ashogan, researcher, Department of Chemistry and Chemical Engineering, Chalmers University of Technology, Sweden, deliberated on recent advances in perovskite solar cell devices. And he discussed about the fabrication of devices for studying the photovoltaic behavior. Dr. Smugul Karasnav, Senior Researcher, Solar Energy Department, Institute for Energy Technology, Norway, explained vividly about the emerging class of materials called mixed anion materials in his lucid lecture, overviewing their attractive applications in smart windows, medicine, photocatalysis, and energy storage devices. The invited talk of the final technical session of the conference on today was delivered by Dr. R. Nanda Kumar, Associate Professor, Department of Applied Chemistry, Karunya Institute of Technology and Science, deemed to be University Coimbatore. He dealt about the applications of modular fluorocolorimetric chemosensors using organic materials as precursors. Professor briefed about the designing of various novel heterocyclic organic fluorophores and ionophores encompassing versatile functionalities. Dr. S. Nirmala, Principal, PSGR Krishnamal College for Women, delivered the welcome address in the valedictory session and introduced the Chief Guest, Professor S. Balakumar, Director, National Center for Nanoscience and Nanotechnology, University of Madras, Chennai. The Chief Guest enlightened the participants with his declamation on multifunctional nanostructured bioactive materials based composites towards biomedical applications. Around 100 abstracts were received from the researchers of various states of India and abroad. Due to overwhelming response, parallel oral and poster presentations were also arranged. A total of 50 oral and 30 poster articles were presented by the selected participants covering interdisciplinary topics of science streams. Notable professors from chemistry and physics disciplines chaired the oral and poster presentations. Invited talks on innovative areas of research by the eminent speakers was circumstantial, loaded with fullness of details. Unique and specific topics were covered with renowned resource persons during the conference. The participants expressed their affirmative feedbacks, insisting the informative, novel, clarity, new ideas, and facts of the presented plenary talks. Live streaming of the inaugural session, Facebook page of the institution, college website, and YouTube live streaming of all the sessions are also the highlights of the conference. Thank you.
Thank you, ma'am.
Gratitude is the fairest blossom which springs from the soul. As we come to the close of our valedictory ceremony, I invite Dr. D. Nalini, Assistant Professor and Head, Department of Chemistry, PSGR Krishnamal College for Women, to propose the vote of thanks.
Honorable guest of the day, Dr. N. Yashoda Devi, Secretary, Dr. S. Nirmala, Principal, and Professor S. Balasubramanian, Director, Office of International Relations from PSGR Krishnamal College for Women, the dignitaries from the University of Dar es Salaam, Tanzania, our most esteemed speakers from all over the world, delegates, colleagues, friends, and students. Good afternoon to one and all connected together. I feel honored and privileged to propose the vote of thanks on behalf of PSGR Krishnamal College for Women and University of Dar es Salaam. This is the proudest day in the history of our college. Today, we have hosted the momentous education conference, Breakthroughs and Approaches in Contemporary Scientific Research, in collaboration with the University of Dar es Salaam, Tanzania, with 10 delegates and 200 participants across all streams of education from science to technology to research. At the outset, I thank our Managing Trustee, Sri G. Rangaswamy, and Chairperson, Dr. R. Nandini, for being the solid support in the conduct of this virtual conference. I profoundly thank our Secretary, Dr. N. Yashoda Devi, and Principal, Dr. S. Nirmala, for their guidance in all our endeavors. I am very much thankful to Professor S. Balasubramanian, Director, Office of International Relations, PSGR Krishnamal College for Women, for his inspiring mentorship, continuous support, which have greatly helped towards the successful conduct of this conference, and also for taking the initiative
for the live broadcast of the event for the benefit of a wide audience. I thank Professor S. Balakumar, Director, National Center for Nanoscience and Technology, University of Madras, for an exclusive valedictory speech. My heartfelt thanks to Professor Thomas Limo, Principal, College of Natural and Applied Sciences, University of Dar es Salaam, Tanzania, for his felicitation during the inauguration of the conference. I extend my heartfelt thanks to all the resource persons, Professor Muthupandian Ashok Kumar, International University of Melbourne, Australia, Dr. R.L. Gardas, Indian Institute of Technology, Madras, Dr. Vijay Shankar Ashokan, Chalmers University of Technology, Sweden, Dr. Smegal Karasnov, Institute for Energy Technology, Norway, Dr. R. Nanda Kumar, Karunya University of Institute of Technology and Science, Coimbatore, and Dr. Grace A. Kinenda, Dr. Litiko, Dr. Kezi, and Dr. Nuru from University of Dar es Salaam, Tanzania, for sharing their expertise and sparing their valuable time for the past 3 days. I extend my thanks to Dr. Kezi, Senior Lecturer and Head, Department of Chemistry, and Dr. Nuru Miluka, Senior Lecturer and Head, Department of Physics, University of Dar es Salaam, Tanzania, for their enormous cooperation in organizing this conference. I wholeheartedly thank Dr. P. Meena, Associate Professor and Head of the Department of Physics, for joining hands with me to convene the 3 days of international conference. I heartily congratulate the organizing secretaries, Dr. J. Balavijayalakshmi, Dr. S. Shanmugasundari of Physics Department, Dr. N. Muthulakshmi Andal, and Dr. N. Anisha of Chemistry Department, PSGR Krishnamurti College for Women, Dr. G. Kenenda, Dr. Clarence from Chemistry Department, Dr. Samiji of Physics Department of University of Dar es Salaam, Tanzania, for their meticulous effort in putting together for this conference to a grand success. I thank Dr. Clarence Migna, University of Dar es Salaam, Dr. S. Ponpandian, Bardiyar University, Dr. Punnuswamy, Government Arts College, Coimbatore, Dr. R. Vasanta, Anna Adarsh College for Women, Dr. S. Ramesh, Dr. G. Sylvie, and Dr. G. N. Priyadarshini from PSGR Krishnamurti College for Women for chairing their 9 parallel technical presentation sessions. Dear all, an event like this cannot happen overnight. The wheels start rolling weeks ago. It requires planning and a bird's eye for details. We have been fortunate enough to backed by a team of very motivated and dedicated colleagues of the Department of Chemistry and Physics, PSGR Krishnamurti College for Women, who know their involvement and their willingness to take on the completion of tasks beyond their comfort zones. My thanks also go to all the people who have given their precious time in organizing the conference. I acknowledge all the active participants from all over the country for their enthusiastic participation throughout the conference. I thank Wing Commander V. Ganesan and Mr. Venugopal and his technical team from Krishnamurti College, India for their technical support. I thank all the research scholars and the student coordinators of Department of Chemistry and Physics for their active involvement in the conference. Once again, I thank each and everyone who put together their hands to make this conference a grand success. Thank you all.
Thank you, ma'am. The end of a story is the new beginning for many others. On this note, let's conclude the memorable and knowledgeable valedictory session. We sincerely thank each and everyone for being with us these 3 days in this learning process. National Anthem.
Ibariki जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे।
Thank you all. Everyone is free to leave the meet.
Thank you all. Everyone